Today's topic is the fine structure of the hydrogen atom. So, fine structure, hydrogen fine structure. Last time we discussed spin-orbit coupling and the Thomas precession, and to get the correct value we needed a factor of 1/2 Thomas factor. We talked about it in the last video, and this was a purely relativistic kinematic effect. So spin-orbit effect is basically a relativistic effect, and let us remember it's just that electron is a magnet, small magnetic dipole, and electron feels the proton current about it, and the proton current generates a magnetic field, and the electron magnetic moment interacts with it. And when you transform it to the inertial frame, which we take as the proton frame, you need a factor of 1/2. So this brings us to the question of are there other relativistic effects? And the answer is yes. So we shall today, this is a preview of what's to come today. Relativistic kinetic energy. The change in the energy eigenvalue due to the relativistic correction to the kinetic energy. This one is telling us that we will use the first order perturbation theory. Second, there is another thing, delta E1 Darwin. This is also a relativistic effect. And we shall go very shortly over the spin orbit again, just rewriting the results. And we will also see that the spin orbit effect is operational only when L not equal to 0. However, for L equals going to 0, the spin orbit goes to delta Darwin. So we shall look at that. And fourth, we will add them up. The addition will give us the energy shift due to the fine structure, namely the relativistic effects, basically to power alpha 4, alpha being the fine structure constant. So this will be the sum of delta E1 relativistic kinetic energy plus delta E1 spin orbit plus delta E1 Darwin. And I will show the compare the graphs of these things. So we will study the components graphically. And fifth, we will write the Dirac eigenvalue, and we will expand it to order alpha to the 4th and compare the result with the fine structure constant. So this constitutes what we will do. First, I'm starting here. Correction due to the relativistic kinetic energy. So the kinetic energy operator will be like this. M square C to the 4th plus P operator square C square minus MC square. This is the correction to the non-relativistic P operator square over 2M term. All right, but still MC square is much larger than P operator times C, and therefore we expand this thing. So let's write it mc square 1 plus the operator square c square over c to the fourth 1/2 minus mc square. So this cancels that. Square c square. Let's call it x, and we will expand in the binomial series. Beta in general will be 1 plus beta x plus 1/2 beta minus 1 x squared plus. For beta non-integer, this is an infinite series. Okay, our x is here. X is an I don't mean the coordinate x, just p operator square over m square c square. So kinetic energy operator equals mc square one plus beta is 1/2 here, 1/2 times p operator square over m square c square plus 1/2. Beta is 1/2. Let me write here. Beta here is 1/2. Another 1/2. 1/2 minus 1, that's minus 1/2. X square. So it is p operator to the fourth, m fourth, c fourth, plus it goes on like this, minus m square, mc square, the rest mass energy. So this mc square and that mc square cancel. So they cancelled. So the first term is p operator square over 2m. So this is the traditional non-relativistic kinetic energy. Let's continue. Next, this I have 1 over 8 p operator to the fourth over m cubed c square. M cubed c square plus dot dot. All right, so our relativistic kinetic energy correction is minus 1 over 8 p operator to the fourth over m cubed c square. All right. Now, we need black board space, so I will erase everything here. So, with that correction, let us write the full Hamiltonian again. P square over 2m, this is an operator, plus v Coulomb, plus this thing, h prime, relativistic correction to kinetic energy, psi equals a psi. But we will not solve this equation exactly. We will treat this as a perturbation. So this is our H0, the unperturbed Hamiltonian. If you write it in detail, our physical plus H prime relative now when I say our physical, I mean magnitude with dimension length. Remember that we like to turn things around and make them dimensionless, which is much nicer because you don't have to deal with the constants. So our physical, right, R0 or A0 times r. So this is a dimensionless length. In units of this is measured in units of Bohr radius. So this is again h square over 2m r0 square minus times r square delta r square minus e square over 4 pi epsilon 0 1 over r0 times 1 over r plus h prime psi equals e psi. Now, if you remember, in the first lecture of hydrogen atoms series, when we studied the magnitudes, we showed that this was the energy, bound state energy of the ground state, absolute magnitude, and this was 2 epsilon. So let us divide by epsilon. To get minus del square delta r square minus 2 over r plus h prime over epsilon psi is equal to e psi, but we write e as minus because we are talking about bound states which have negative energies, so let's write e psi. So since we divided every part by epsilon, this is divided by epsilon minus e over epsilon psi. So let us look at h prime again. H prime is here. This is now p prime squared. This is the dimensionless momentum. P prime vector is h bar, no h bar, 1 over I d by dr. So the square is that. And p square over 2m here, p square over 2m, we have shown that it is epsilon times p prime square. Epsilon times p prime square. So p, I want to write this p operator to the fourth in terms of this p prime that I have now written in dimensions. Therefore, p square is 2m epsilon p prime square. Therefore, h prime over epsilon, I'm taking this, that's equal to minus 1 over 8 epsilon. This epsilon comes because I divide by epsilon. P operator to the fourth, this is 4m square, epsilon square, p prime to the fourth, divided by m cubed c square. M square cancels power of 2, so I have mc square. So it is minus 1/2. Epsilon cancels that. I have a term epsilon over mc square. Epsilon over mc square times p prime to the fourth. So this is a dimensionless momentum. Clearly, h prime has units of energy. I am dividing by energy, so this is dimensionless. So epsilon is the bound state of the ground binding energy of the ground state, which is positive 13.6 electron volts. mc square is 1/2 MeV. And however, this has a nice formal expression because epsilon, if you remember, we wrote it as m e square over 4 pi epsilon 0 square over 2h bar square, 2h bar square. So to get to epsilon over mc square, I multiply c squared divided by c square. Therefore, epsilon over mc square, if you recall, e square 4 pi epsilon 0 divided by h bar c is just the definition of alpha, the fine structure constant. So this is alpha square over 2, alpha square over 2. So it is minus 1 over 4 alpha square p prime to the 4th. I can erase this part. Therefore, I can write the Schrödinger equation again in this form. H0 and then minus 1 over 4 alpha square p prime to the 4th will be equal to minus v over epsilon times psi equal to that. Whereas H0 is p prime square minus 2 over r is our dimensionless unperturbed Hamiltonian. And we know its eigenstates and eigenvalues, the energies. All right, now we'll make a perturbation. Therefore, delta E1 will be simply the expectation value of this operator. So it is minus alpha square over 4 p prime 4 average. All we have to do is to compute this expectation value. And the form of the perturbation is simple because we can obtain it from here. By the way, let me write H0 psi 0 n is E0 n, I will call physical psi 0 n. This is the result of the unperturbed problem, and we solved this problem in the previous videos. E0 n physical is negative E0 n, which is minus epsilon over n square. Epsilon is the binding energy of the ground state, the absolute value of the binding energy. So the eigenvalues and eigenstates of H0 are known. Now we can compute p prime 4 from here. As you see, p prime square is H0 plus 2 over r, and p prime 4 equals H0 does not commute with 2 over r because we have a p prime square that doesn't commute with. So we have to be careful in the order. We have H0 square, so I'm just squaring this, plus 2 H0 1 over r plus 2 1 over r H0 plus 4 over r square. And I have to sandwich it between the states, eigenvectors, that thing. So we will since these states are eigenkets or eigenbras of the H0, this part is easy. Then we have the expectation value of 1 over r and 1 over r square. So I will write it here, but first I have to erase. I'm going to take this thing, but I wrote this wrong. This is not the scaled, because this is the physical energy in units of energy. This is the full H0. All right, it's the full H0. So H0 psi 0 n, it is divided by epsilon, so there is no epsilon. It is minus E0 n psi 0 n, and this is simply 1 over n square. So H0 is, again, H0 over epsilon. Okay. So, all right. Now I will compute the average of P prime 4. The first term is minus E0 n square. Then each of them gives me minus E0 n. So I have minus 4 E0 n times the average of 1 over r. Then I have plus 4 times the average of 1 over r square. Square of minus is plus. This is simply 1 over n square, so this is 1 over n to the 4th minus 4 1 over n square 1 over r plus 4 1 over r square. These are the averages of the dimensionless distance r, or physical distance measured in units of r0. So this is, we computed in some of the videos before. This is 1 over n squared. This is 1 over n cubed l plus a half. So we just add them up. This is minus 3 over n to the 4 plus 4 over n cubed l plus a half. So this is P prime 4. We will multiply it by minus alpha square over 4. Therefore, delta E1 relativistic correction to kinetic energy is equal to minus alpha square over 4. So I'm multiplying it by minus 1 over 4. So it is, let me do it like this. I take 1 over n square out, and I have alpha square over n. You will see why I'm doing that. Alpha square over n. This is 1 over epsilon. N square over. I'm multiplying it by minus 1 over 4. So 3 over 4n, this is plus now, 3 over 4n minus 1 over 4 cancels that. N cube is out, 1 over l plus a half. I am finished. Let me write it cleanly. Delta E1 relativistic correction to kinetic energy is, if I remember, epsilon over n square is E0n, the absolute value. For example, if n equals 2, this is 3.4 electron volts. Now it has the units of energy. E0n times alpha square over n times 3 over 4n minus 1 over l plus a half. Finished. We have computed the And again, let me remind you, epsilon over mc square was equal to alpha square over 2. So epsilon is mc square alpha square over 2. So E0n is epsilon divided by n square. So this is already to alpha square. So this is basically an alpha to the 4th term. All right. So this is the result. We will now investigate this result a little bit. So I need the blackboard. I am erasing. I want to look at the second term. 3 over 4 n minus 1 over L plus 1 over L plus a half. Now, n takes on the values integers, and L for a given n can be 0, 1, up to n minus 1. So the minimum L minimum, which is 0, so this parenthesis becomes 3 over 4n minus 2. Now, n is at the smallest 1. So this is either 3 over 4, 0.75, or even smaller. So it is minus 2, so this is negative. L max, maximum value n can take is n minus 1. So let's look at it. 3 over 4n minus 1 over n minus 1. N minus 1 plus a half. So it is n minus 1 half. So it is 3n minus 3 over 2 minus 3 over 2 minus 4n. 4n divided by 4n n minus a half, which is minus n minus 3 halves for n minus a half. So n minus, since n is 1 or more, this is always positive, this is positive, so denominator is positive, and this is always negative, minus 3 over 2 minus n. So this is also negative. So the relativistic kinetic energy correction here is always negative and depends on n and L. All right. In all these corrections that I mentioned at the beginning, for numerical estimate, let us take the n equals 2 and L equals 0 and 1 levels of hydrogen. All right. I will call this factor here an. So let's look at how big is A2. A2 is equal to E02 times 1 over 2 times alpha square. Alpha square. E02 absolute. This is 3.4. 3.4 electron volts divided by 2. Alpha square is 1 over 137. 137. Let us make it 140. We are trying to estimate. So this is 1.7 divided by, this is like 1.96 10 to the 4. So say 196 is 2. This is equal to 1.7 times 10 over 2 is 5 times 10 to the minus 5 now. This is like 8.5 times 10 to the minus 5. Say that this is 10. So this is like 10 to the minus 4 electron volts. So A2 is roughly 10 to the minus 4 electron volts. You see, it's really a small correction because it's coming of order alpha square. The energy is like electron volt for the unperturbed energy. So the correction is coming like of order 10 to the minus 4. Let's look at the other terms. N equals 2, L equals 0, delta E relativistic kinetic energy over A2 is equal to 3 over 4 times 2 minus 2. So what's that? This is 3 over 8 minus 16 over 8. So it is minus 13 over 8. And L equals 1. Delta E relativistic over A2 is equal to 3 over 8. But this time 1 plus 1/2, so it is 3 over 2 minus 2 over 3. So it is 9 minus 16 divided by 24. So it is minus 7 over 24. And let's, to make the comparison, let's make it multiply by 3 upstairs and downstairs. So it is minus 39 over 24. The best thing is to plot. I don't need these anymore. This part I am erasing. So let me write delta E1 over A2. Let it be 0. So it is, here I have so if you are at 0, that means you are at the, this corresponds to the minus 3.4 electron volt. The question is how far we go above or below this second state energy. So this is, you see, it doesn't depend on J, it's really depending on L. All right, so we can use the J states. Let me say here, 2s 1/2, 2p 1/2, 2p 3/2. These are the states of the unperturbed Hamiltonian. Here we have now H0 plus H prime. So let me go by 7 centimeters. Here I have colors for you. And this is 2p 1/2, 2p 3/2. And we'll go by 39. This is the 2s 1/2. So let us look at the corresponding energies. This is like A2 is 10 to the minus 4 electron volts. So 1 over 24 is like 1 over 25 is like 0.04. Here I am multiplying by 7. So it is minus 0.3 times 10 to the minus 4 electron volts, shifted below the unperturbed energy of minus 3.4 electron volt of n equals 2 level of hydrogen. And this one, this is shifted way down to S 1/2. So it's like 40 times 0.04. This is like 160, 1.6. So it is the energy would be minus 1.6 times 10 to the minus 4 electron volts. So this is the energy shift due to the relativistic correction of the kinetic energy. Sometimes you see these differences in terms of given in terms of inverse centimeters. And you can, so for example, if it is x inverse centimeters, if you see in some books, spectroscopists sometimes give it that way. So you have to multiply it x centimeter inverse. Here is a number, so many. Then you multiply by 1, 2, 4, 1 times 10 to the minus 4 electron volts centimeters. So centimeters cancel. So you have x times this times 10 to the minus 4 electron volts. So you can convert from electron volts to from inverse centimeters to electron volts. Okay, so this is the correction due to the relativistic correction to the kinetic energy. All right, after the relativistic correction to the kinetic energy, we will consider another term which with origins in relativity, and it is this term. This is called the Darwin term. And how did we get it? It doesn't come from non-relativistic mechanics. It comes in the non-relativistic reduction of the Dirac equation. So to this order, we get such a correction term in the Hamiltonian. So this is directly coming from the Dirac. Okay, it's one of the terms in the non-relativistic reduction of the Dirac formalism. All right. So again, when I say R physical, I mean distance, like centimeter or in angstroms. So this I can also write as h prime d is equal to 1 over 8 lambda bar square delta square v. This is the reduced Compton wavelength, and it comes about like this, the meaning of the Compton wavelength. If the rest mass energy is if the photon energy is the rest mass energy, then we have h over lambda times c, and Compton wavelength is defined as h over mc, and you divide it by 2 pi, 1 over 2 pi, we multiply. Therefore, lambda bar is equal to h bar over mc. All right, so let us look at this. Remember, we are making things dimensionless. So it is 1 over 8 lambda bar square times this thing. Minus is plus. So I have e square over 4 pi epsilon 0 from here. And then I have 4 pi delta r physical. But r physical is r0 times r. It's 3 dimensions. Therefore, this thing is 1 over r0 cubed delta r. And we can make these combinations 1 over 8 lambda bar over r0 square so r0. Then I have e square over 4 pi epsilon 0. I have divided by epsilon, so let me just divide by epsilon also. 1 over r0. Then 4 pi times delta r. This much is, we know from the first lecture in the hydrogen atom series, that this is the energy through epsilon, just like we did in the beginning of this lecture. So this epsilon is cancelled. So I have 8 pi here and 8, so this only leaves a pi. Let's look at this term. R0 is, that's the Bohr radius, is h bar square over m e square over 4 pi epsilon 0. So if I divide by h bar c, divide by this h bar c, this is h bar over m, and e square over 4 pi epsilon 0 divided by h bar c is alpha. Therefore, R0 times, or let me write like this, this is lambda bar over alpha. Therefore, lambda bar over R0 is alpha. So this is equal to 1 over 8. 8 is cancelled with 2 times 4. So I have only pi. Here I have alpha square and delta r. So this is my dimensionless Darwin Hamiltonian. So the energy correction of this operator will be computed by the first order perturbation theory. So I need to erase something. All I need is this. I'm erasing all the rest. Okay. So delta E1 Darwin over epsilon, that's equal to h prime d divided by epsilon, and pi alpha square delta r. I can erase this one. All right. Now, take, for example, if you are considering dr f of r delta r, this is simply f evaluated at 0. So instead of f, I have psi n lm square. So the result is r n l 0 square and square of the angular function. But r and l vanish for l not equal to 0. So the only term that survives is the s terms, l equals 0 terms. So this is equal to delta L 0 r n 0 square at 0. And the angular function with L equals 0 is YLM, so it is y0, 0 square. So let's look at Rn0 square. The normalization coefficient square, these chalks, n0 square. Then I have an exponential evaluated at r equals 0, which is 1. Then I have L, remember, this is L, 2L plus 1, and minus L minus 1. But now I have L equals 0, so it is L 1, L is 0, so n minus 1 evaluated at 0. For associated Laguerres, we took the normalization of the Laguerres in our approach. Remember, there are various normalizations of the Laguerres, each related by a constant. Ours is if alpha and r constant are integers, then this is alpha plus n factorial divided by alpha factorial n factorial. And in our case, L1 n minus 1 0 equals 1 plus n minus 1 factorial, 1 factorial, n minus 1 factorial, which is just n. And n and L square was 1 over n over 2, 2L plus 3, 2n, n minus L minus 1, n plus L factorial divided by n minus L minus 1 factorial. Therefore, n0 square is equal to 1 over n over 2, L equals 0, so it is cubed, 2n, n factorial, L equals 0, n minus 1 factorial, so it is n. This is 8, so 4 over n to the 5 square. So this is 4 over n to the 5 times n square. That's equal to 4 over n cubed. So I'm coming to here. Y0, 0 is 1 over 4 pi. So delta E1 Darwin divided by epsilon is equal to pi alpha square times this. This gives me first delta L equals 0. Only it works effectively with L equals 0. Then I have 4 over n cubed. 4 over n cubed times, coming from the radial, times 1 over 4 pi, coming from the y0, 0 absolute square. That's it. So 4 pi's cancel. Therefore, I can write delta E1D. That's equal to, first, it's operative only when L equals 0. Then I have epsilon over n square. Then alpha square over n. So this is our coefficient an times 1. That's it. Let me just plot the correction. Remember, before when we did the relativistic kinetic energy correction, we had terms like 7 over 24 and 39 over 24. So let's write this as 24 over 24. And this is delta E1 over A2. Remember, I am doing it for n equals 2, L equals 0 and 1. So this is 0. This is where everybody is. Get my the sign is plus, so I must go up. So here there were, in the unperturbed case, 2s, let me write it white, 2s 1/2, 2p 1/2, 2p 3/2. This is H0, unperturbed hydrogen, just p squared over 2m, non-relativistic kinetic energy plus the Coulomb. Now the effect of the Darwin term, it is operative only on the L equals 0, so only shift is 2s 1/2, and the others are here. The others are not affected. 2p 1/2, 2p 3/2. We are essentially done with the Darwin. However, I want to add something, and it is this. Remember that this is directly coming from the Dirac equation. However, we can, I'm not saying derivation, we can make a plausibility and simulate this effect in some way, which I will explain now. I'm erasing it. So plausibility argument and simulation. The argument is this. What's the meaning of the Compton wavelength? It means that you can take a sphere of radius lambda Compton. Of course, this is not a sharp sphere. We don't really exactly know. These are just order of magnitude things. It says that within the Compton wavelength, within a sphere of radius of Compton wavelength, we cannot really know where the electron is. And this is also related to the Zitterbewegung motion of the electron in this relativistic Dirac theory. So if we don't know where it is, we should not use V of r, but we should average V of r within such a sphere. Now, so for example, if we should not consider V of r at this point, but we should take V of r plus a and average it over inside a sphere of radius. This is important. What's the radius of that sphere? Because these are just order of magnitude computations. And let me write this sphere radius b times lambda. B is a dimensionless, it's a pure number. Lambda is the reduced Compton wavelength. Why am I writing it? Because I have it here. All right. So I will use the average of V of r plus a. So I am computing the average within this sphere. So V R plus A, which I define as dA, the volume dA, VR plus A divided by the volume. Volume, we know what it is. Volume is 4 pi over 3 r cubed, radius cubed. This is b lambda cubed. So we will again do approximation, expand this. So VR plus A. Remember, V of R is just the Coulomb force. V of R, which is V of R. Or let me write it in a way that will become useful here. V of R plus A at A equals 0 is V of R. All right, so the first term will be V of R. The second term will be A. Now, I will not write V of R plus A evaluated at A equals 0. I will simply write V of R plus the second order term, V of R. I am entitled to do this because this is already to second order in A. So I'm erasing this part. Anyway, this result is easy to remember. It is AN times 1. Let me write it here. Delta ED1 is equal to AN for all this. Delta L equals 0 times 1. And I'm erasing it. So we put this into the integral. So the first term gives me V of R times volume divided by volume. So I have only V of R. Plus 1 over volume. Now, I have dA, A, dotted into del, which is V of R, plus 1 over volume times 1 over 2, then dA, AI, AJ, then I have d by dxi, d by dxj, V of R, summed over I and j. Sum is because of the dot products. So the first term is V of R. What's the second term? This is clearly a vector. However, the volume that we are integrating A is a sphere. But vector has a direction. Sphere is, all directions are equivalent. So we expect this integral to be 0. So if I call this vector f, for example, let me just take the dot product of f with any vector. And let this is, of course, dA, A dot B. B is not integrated over, it's a fixed vector. And for convenience, let us take the B along the z-axis. Therefore, AB is simply AB mu. And this integral is d phi d mu. Mu is cosine theta from -1 to +1 mu. Then the radial integral. But this integral is 0 because from -1 to +1, we are integrating an odd function, so it is 0. So this term is 0, as expected, because over a sphere we don't expect a direction. Now, what about this one? This is now a tensor Fij. let us look at the components of A. Ax is just like in the spherical coordinates. It is A sine theta cosine phi. Ay equals A sine theta sine phi. And Az is A cosine theta. Now, consider, for example, Ax-Az integral. Ax-Az integral here. Ax-Az integral will have a cosine phi term. So cosine phi term changes like that. So it is plus minus plus with, so it is 0. Namely, d phi cosine phi over the interval of 0 to 2 pi is equal to 0. Ay, Az, I'm looking at the phi integral. Y has sine phi, therefore this is so plus and minus, so this will give me 0. All right, then I have Ax, Ay term, Ax, Ay. But this has cosine phi, sine phi, which is sine 2 phi. So, right? So it is plus, minus, plus, minus. So this will give me 0. So if I is not equal to j, I get a 0. Therefore, I have a tensor Fij if I is not equal to j, it is 0. So therefore, it is some strength times delta ij. And certainly delta 1, 1, delta at different directions, it's not going to be different because it is over the sphere. So how to compute this A? Let us take the trace F. Trace F is equal to A times trace delta, which is just 3. So trace F is what? Trace F is equal to dA trace F means set I equals to j, then sum. So ax square plus ay square plus az square, which is just a square. So the angle integrals give me 4 pi. Then I have from 0 to b times lambda, that's the radius, times dA, a square, and another a square. So it is 4 pi over 5, b lambda to the 5. Let me divide by 3, multiply by 3. 4 pi over 3, b lambda cubed is the volume. So I have a volume times b lambda square times 3 over 5. 3 times 5. That is equal to 3 times A. I took this one as the volume. So this 3 is gone. So A is cancelled, 3 is cancelled. So A is this. Just that. So let me erase, let me continue under here. So it is 1 over volume 1/2 A times delta ij. So A is volume, B lambda square over 5. So I wrote 1/2. This is A. And now I have del square V. Because I is equal to J and I am summing over. So volumes cancel. So if I compare it now with this one, this is coming from Dirac. What do I have now? So H prime, Darwin, some simulation or plausibility argument gives me 1/10 5 times 2 is 10 B lambda square coming from here and del square V. So if you compare the strength, 1/8 lambda square is equal to B square. So these things cancel. B square is 10/8 or 5/4. It is 1.25. And B is something like 1/12 or something. The point is this. I'm not saying that we have derived the Darwin term. We have just tried to understand the physics behind it. Namely, if you in very small volumes, volumes smaller than the Compton wavelength, we really can't point the electron there. It's not certain. So it is this uncertainty sort of smears it out, and we get the form right. And we almost get the B square is not B square is not 1/8, but 1.25. No, sorry. B square is not is not 1 or something. The point is that the radius is not fixed, so it's a sort of like a phenomenological parameter here, and so that doesn't make it exact. Okay, the exact form is what's coming from the Dirac form, but this is just a plausibility argument that it is entirely due to not being able to locate the electron within the sort of the Compton within a sphere of whose radius is of the order of Compton wavelength or reduced Compton wavelength. All right. Well, the third case, correction due to the spin orbit. If you remember, we already done this, and this was the result we obtained and which we further analyzed. I just want to bring it to the form to make the comparison with the other two. So let's say delta E1 over epsilon is 1/2 epsilon. GS over 2 is just like 1. I cancel this, so it is H bar square over MC square bar mc square times, this is now 1 over r0 cubed, 1 over r cubed. This is dimensionless, this is the Bohr radius. So I have E square over 4 pi epsilon 0. I have 1 over r0 square. Bring another 1 over r0 here. Then I have 1 over r cubed L dot S. So this part is 2 epsilon. So they cancel. Remember that when we discussed the Darwin, we found R0 alpha was equal to lambda bar. Therefore, this is lambda bar square. So lambda bar square over R0 square is simply alpha square. So this is equal to alpha square times 1 over r cubed L dot S. 1 over r cubed, we computed this average. It was 1 over n cubed, 1 over L. It's easy to remember because it increases by 1/2, L plus 1. Therefore, let me write it like this. Delta E1, spin orbit. Delta E1, first order perturbation, spin orbit is equal to epsilon over n square is the absolute value of the hydrogenic energy level of the level n. Therefore, it is E0n. Epsilon over n square is E0n times alpha square over n. So this is our coefficient an. Now L dot S, you see this operator is now acting on the spin. Neither the Darwin term nor the kinetic energy, relativistic kinetic energy correction acted on the spin. So it didn't matter. But now we have to use the functions that are linear combinations that are eigenstates of it, which we did last time. And we know the result. This is 1 over this now, L plus a half, L plus 1 times 1 over 2. I'm writing this 1 over 2 times L, or minus 1 over 2 times L plus 1. This is for J plus, which is L plus a half, and this is J minus, which is L minus a half. So again, and remember this L is not equal to 0. The spin orbit term is exactly 0 for the S waves. All right, so let me write here again. Delta E1 spin orbit is equal to AN, it is this term, times 1/2 L's cancel, 1 over L plus a half, L plus 1, and minus 1/2. L plus cancels this, 1 over L plus a half. This is for J plus is equal to L plus 1/2, and this is for J minus, which is L minus a half. So let me plot these. Here's the I'm erasing this part. Of course, let us plot it for, again, n equals 2. So I have either L equals 0 or L equals 1. But now for J plus, I have L plus 1/2. And J minus is equal to L minus 1/2. But L equals 0 is not to be used because spin orbit coupling is 0 for the S wave. So we only have the L equals 1. So delta E1 spin orbit divided by A2. Remember, A2 is like 10 to the minus 4 electron volts. So it is 1 over 2, 1 over 3/2, and 2 equals 1 over 6, and this is J plus, which is 2p 3/2 state, p 3/2 state, or 1/2 minus 1, that's 3/2, minus 1 over 3. Since the other ones, we will make the comparison. We're getting 1 over 24, so this is 4 over 24. And this is minus 8 over 24. This is the 2p 1/2. So let me plot this. This is delta E1, spin orbit divided by A2. All right, this is my red chalk. So with the unperturbed, everybody is here, all the states. 2s 1/2, 2p 1/2, 2p 3/2. They are all degenerate and here. But with the spin orbit turned on, 2s 1/2 is not affected. So this is 2s 1/2. This goes 4, and this goes 8. So this is 2p 3/2, 2p 3/2, and 2p 1/2. And how big are they? Their energies. This is 1 over, say, 25. So it is 0.04 times 4. That's 16. 0.16 times 10 to the minus 4 electron volts, and this is minus 0.32 times 10 to the minus 4 electron volts. You should read this as upon the unperturbed energy of the n equals 2 level. We call it 0, but this is the shift from the unperturbed state. So the energy of the unperturbed state is at minus 3.4 electron volts. So we are done with the spin orbit, except I would like to draw your attention to this. In this spin orbit term, this is exactly 0 for L equals 0. And if you just take it, we wrote it somewhere here, because L goes to 0, this becomes infinity. So it's like infinity times 0. There is an indefiniteness. This is, however, no longer there if Dirac equation is correctly handled for this limit, and this becomes large but finite, but this is exactly 0. So there is no spin orbit term for L equals 0, period. No spin orbit for L equals 0. And we have a Darwin term which operates only for L equals 0. But now look what happens. If we just take, I can erase this small part. If we just take like a mathematical game, the limit L goes to 0 of the spin orbit term, which is the, in this case, we have only J plus, because J plus is L plus a half. J has to be a positive half integer or integer. L, if it's 0, you have 1/2. J minus with L equals 0 will be minus a half, which is not allowed. So only J plus. So that means we look at upstairs. The L here cancelled that L, and we have for L equals 1, L equals 2, etc. we have something finite. But suppose you take it to 0. You take L equals to 0. So let me divide by AN. So this is delta E1 spin orbit divided by AN for J plus. Look at what happens. This is 1/2 times L equals 0. I'm looking at here. 1/2 L equals 0, 1/2, and you have 0 here, so it is 1. So it is simply 1. So limit L goes to 0 of J plus, which is L plus a half of delta E1 spin orbit, simply goes to AN times 1. And remember, this is delta L equals 0. So this is exactly the same thing as delta E1 Darwin. So that we can write, I don't need these anymore, I'm erasing. Ordinarily, we would do it like this. We would write delta E1 spin orbit 1 minus delta L 0. So when L is not equal, this operates when when L is not equal to 0. So when L is not equal to 0, this is 0. So we have the usual spin orbit term. And when L equals 0, we have the Darwin term, delta E1D, delta L 0. But we have shown that this is the limit L going to 0, delta E1 spin orbit with J plus. So that, let me call this now delta E tilde 1 spin orbit. This will now include, now we can combine it, this one and the Darwin term. So with that understanding, we will keep it L equals 0 within the spin orbit term, except that we understand it like this. There is no spin orbit term for L equals 0, except that for L equals 0, the spin orbit term for the J plus expression goes to the Darwin term. Of course, the root of this is clear. It's the Dirac equation. All right. Now I will erase the blackboard, and then we will just add all these expressions we obtained for in terms of J plus and J minus. So I'm erasing it. All right. So we have seen 3 relativistic effects that contribute to a fine structure of order of 10 to the minus 4 electron volts. We have the relativistic correction to the kinetic energy, spin orbit term, and the Darwin term. And when I write tilde, that means we made a combination of the Darwin term and the spin orbit term. All right. This is what we obtained. I'm dividing by AN. This is the relativistic kinetic energy divided by AN. We had obtained this at the beginning of this video. And then for the spin orbit, remember tilde means I have the pure spin orbit plus the Darwin. It is that. And let's now transform these things to J and sum. So J is L plus a half. So this is 3 over 4 N minus 1 over J. So J here is J plus. This one is 1 over 2. L plus a half is J. L plus a half plus a half. So it is J plus a half. That's equal to 1 over J, 2J plus 1. We add them up. Delta E1 fine structure divided by this AN. That's equal to 3 over 4N minus 1 over J plus 1 over J, 2J plus 1. That's equal to 3 over 4N, 1 over J parentheses, plus 1 over J, 1 over 2J plus 1, minus 1, so, minus 1. So this is 1 minus 2J minus 1 divided by 2J plus 1. So 1's cancelled. So this is equal to 3 over 4N minus 2J over 2, 1 over 2J over J, 1 over 2J plus 1 equals, so J is cancelled. I divide by J, this is J. So it is 3 over 4N minus 1 over J plus a half. This is for the J plus. Therefore, for J plus, delta E1 fine structure over AN is equal to 3 over 4N minus 1 over J plus a half. Now we will do the same thing for J minus. I'm erasing this part. This only depends on L, and for this one, I have to change it. Minus 1/2, 1 over L, L plus a half. All right. This time, however, J is equal to J minus, which is L minus a half. Therefore, L is J plus a half. So it is equal to 3 over 4N minus J plus a half minus 1 over J plus 1. this is equal to minus 1 over 2. L is 1 over j plus a half. And j plus f, this is j plus 1. So we add them, an, 3 over 4n minus 1 over j plus 1 minus 1 over j plus 1 2j plus 1 equals 3 over 4n minus 1 over j plus 1 parenthesis 1 plus 1 over 2j plus 1 equals, this is 2j plus 1, so it is 3 over 4n minus 1 over j plus 1, 2j plus 1 divided by 2j plus 1. So j plus 1's cancel. We again take 2 down. This is 3 over 4n minus 1 over j plus a half. So it's the same result again. J minus is for j minus delta E1 Fs or An is equal to 3 over 4n minus 1 over j plus a half. So it doesn't matter whether you have a j plus or j minus. As long as you have j, that's it. You have only one relation, delta E1 fine structure correction, full fine structure divided by An is equal to 3 over 4n minus 1 over j plus a half. Again, let us look at it for n equals 2. What it is saying, before our formulas were for L. Now we have J. And it only cares about J and not L. The full fine structure shift. Okay? It only cares about the value of J. So n equals 2. L equals 0 or 1. Spin is always. So we have J is equal to 1 half. J equals 3 half. But we have 2 J equals 1 halves. 2S 1 half, 2P 1 half. So it doesn't matter about L. Those those which have the same J will have the same energy. So let me plot the energy here. All right, I erased the computation. So n equals 2. This is, first let's do it for j equals 1 half. So this is 3 over 8 minus 1 half, 1. That's it. Which is 3 over 8 minus 8 over 8. So it is minus 5 over 8. And j equals 3 halves. 3 over 8 minus 3 halves, 1 halves, 4 halves, which is 2, minus 1 over 2. Which is 4 over 8. So it is minus 1 over 8. So let's also go to 24. So it is minus 15 over 24. And this is minus 3 over 24. delta E1 fine structure over A2. This is 0. Okay, now red with H0. Everybody is here. 2s 1/2, 2p 1/2, 2p 3/2. Here, this is 1/2, but that means we have, for this one, 2s 1/2, 2p 1/2, and this is 2p 3/2. So, where is my ruler? That's 3 and roughly 15. So this is 2p 3/2, and this is 2s 1/2, 2p 1/2. As far as the energy goes, remember A2 is like 10 to the minus 4. This is A2. A2, which is E0 to alpha square over 2, alpha square over n, is like 10 to the minus 4 electron volts. All right, so 1 over 24 is like 1 over 24, like 25 is like 0.04, and minus, so it is minus 0.12 times 10 to the minus 4 electron volts, and this is 5 times like minus 0.6 times 10 to the minus 4 electron volts. This is now a fine structure, namely relativistic kinetic energy plus delta E. Now let me write explicitly Darwin plus delta E spin orbit, all computed in first order perturbation theory. So this is the result. Now, I have shown relativistic kinetic energy separately, Darwin separately, spin orbit separately, and this one. Perhaps it's good to see the whole table together. For this, I will need to clean the blackboard, but I will write everything on the blackboard, then we will start the video, because you have all seen the components before. We are only putting them together right now. We have computed the correction numerically for the n equals 2 level of the hydrogen, and these are the results in the tabular form for the relativistic correction to kinetic energy. Darwin term, which is operating only L equals 0, so it's only operating for the 2s 1/2 term and not for these. Spin orbit term does not act on, well, it is 0 for the S waves. So this is, and this is the fine structure. So the best thing is to see in graphs. So I have indicated here what is multiplying 1 over 24. So everybody has a denominator 24, so this is denoting the denominator. So 2s relativistic kinetic energy suppresses the 2s 1/2 level, less so the p levels. Darwin term does not touch the p levels because their orbital angular momentum is not 0, pushes up the s equals 2s 1/2 term. Spin orbit term does not affect the S wave, but spoils the degeneracy here, P3 half is pushed up, so P1 half is pushed down. And finally, when we add them all up, what we have is that 2P, what's that? This is 2P1 half and 2S1 half. When you add them all up, in the fine structure, what we find is that the 2P3 half level is pushed down, and both the 2P1 half and 2S1 half levels are pushed further down, except there is degeneracy. And this is the formula we obtained for the fine structure, which combines relativistic kinetic energy, Darwin, spin orbit terms. And we see that it doesn't care about the L, it cares about J. That's why we have a degeneracy here for the J equals 1 half. Whether we have a 2P or whether we have 2S, they are degenerate. And all right, this is it. I just say one more thing about this thing. They are degenerate when you add them up, all these relativistic effects to the order alpha to the 4 with relativistic kinetic energy, Darwin, and spin orbit. But in reality, these energies are different, a little different. And this is a very small shift. Like these are all of order 10 to the minus 4. By the way, you can get to the electron volt, multiply, for example, here it says 39, minus 39. So minus 39, you are dividing by 24, multiplied by 10 to the minus 4 eV, that's A2. You get it in terms of electron volt, all these energies. This is, however, like this, 2P1 half. This is the famous Lamb shift. And this is like of order 10 to the minus 6 electrons. So it's much, much smaller. So it's a tiny detail. But what a tiny detail. I mean, this little difference in energy opened up a huge field of quantum electrodynamics. Once Professor Lamb of Yale University measured and got the Nobel Prize for it. The understanding of it brought, a new understanding of the fundamental phenomena. Namely, the electron is interacting in all these theories, including the Dirac. Electric field is taken as a classical field, the Coulomb field. But it turns out that electromagnetic field is basically a quantum field, and it has 0-point fluctuations like we did the oscillator. It was the lowest energy was not 0 but 1/2 h bar omega. So the electromagnetic quantum field also has these 0-point fluctuations, and they affect the electron, and it can be measured. And the theory developed to understand this is QED by Feynman, Schwinger, and Tominaga, for which they got a Nobel Prize. All right. So this is the picture. I will clean the blackboard, and then we will do this. Let me just say what we will do. We will write the Dirac energy. We will not derive this thing, but we will simply write it out and then expand it through order alpha to the fourth power of the fine structure constant, and see whether the correction is like this. Or is it the same, or is it a bit different? That's what we will do. Now, if you solve the Dirac equation for the hydrogen atom, you get exactly the energy eigenvalues, and this is J, the total angular momentum of the electron. X is square of the fine structure constant, and the ground state energy epsilon is like that, and epsilon over n square is the absolute value of the binding energy of the level n. In the hydrogen case, this is the bound state energy of the level n. You see that there is a degeneracy in J. Those states having the same J and same n have the same energy. The question is this: if we expand it, this is the exact Dirac solution for the energy of the hydrogen atom. If we expand it, do we get this, or do we get something different? So this is what we will do. So E, this is the Dirac energy, E over mc square. We will write this thing as A0 to the x0 plus A1 x1 plus A2 x2 x square plus, so through, that is A0 plus A1x plus A2x square plus etc. So is A2 this thing? A2 is multiplying alpha to the 4, so there's an alpha square here, there's another alpha square here. So is A2 is all those terms except the alpha to the 4th, or is A2 x square is just the whole thing? Okay, this is what we will do. So let's go slowly because it's a rather complicated expression. And first let's get A0. A0, if you put x equals 0, you get A0. What is A0? We put x equals 0, so if you put x equals 0, this is 0, we get 1. To that limit, A0 equals 1. Therefore, E is only just mc square. That's the free electron energy, basically. How about the next term? A1 term. So, that means if you put x equals 0 here to get to the A1, we will have A, to get to A1, E equals mc square is, to that accuracy, is 1 over root 1 plus x. Now, if you put x equals 0 here, this is j plus a half, which cancels that. So we get n square. And this is roughly 1 minus 1 over 2 n square x. X is alpha square. All right. So A1 here, we read from here, A1 is equal to minus 1 over 2 n square. And to that order, remember A1 is x, which is alpha square. To that order, E equals mc square plus or minus 1 over 2 n square mc square times x, which is alpha square. And 1 over 2 mc square alpha square is here. That's the, so it is equal to mc square minus epsilon over n square, or mc square plus E0 and physical. The physical binding energy is negative, or we can write it as mc square minus E0n. That's the absolute value of the binding energy. yes, the alpha square term is in it, okay, in epsilon. So that's, so far it's easy. The next thing is to get to a2, x square. This time we cannot put this to equal to 0. But let's think of it like this. If we write this 1 over this complicated thing as, suppose I write like this, a plus bx is equal to 1 over n minus j plus a half plus root j plus a half square minus x square. Of course, this is not equal to that, but I want to write this thing as, or let me put it like this, a plus bx. The question is, what is a, what is b? What are they? Well, what is a is obvious. We don't even need to compute, because that's essentially putting x equals 0, and a is 1 over n squared. This is obvious. A equals 1 over n squared. I put x equals 0 here. So these terms cancel. I have the square. It's 1 over n squared. So a is n squared. I put x equals 0. So the question is, what is b? But suppose we will find b. But suppose we find b. What good is this? It will be e over mc squared will be like this. E over mc squared will be 1 over root 1 plus x a plus bx. Let us expand this. Remember, we are expanding 1 plus x a plus bx minus 1/2. We are using the binomial series. First term is 1 minus 1/2 x a plus bx. The second term is plus 1/2. Then I have power. Then I have power minus 1, which is minus 3/2. Then the square of it. X square a plus bx square plus dot dot. So let's collect the powers of x. That's equal to 1. Then the only x dependent term is here. It is minus a over 2x. And a is 1 over n squared. That's okay. Now, how about this square? So for the square, let me write plus x squared. I'm trying to collect the coefficients. I have minus b over 2 from here, minus b over 2. Here plus 3 over 8, plus 3 over 8. You see, I already have x squared. So from here, no power of x should come in. So it's only a squared. So it is a squared. So this will be my a2. So this is a1. And this will be a2. And I already know a. So all I need to know is b. That is expanded to linear power in b. So let me write here this thing, a2 is equal to minus b over 2 plus 3 over 8 a squared. And erase some things so that I have a space. I'm erasing. I'm erasing this. And I want to expand this. to find B. To get to Bx, the strategy will be like this. We will first expand this to linear order in X and then expand it. So this will be, let me call it F. So F will be equal to 1 over n minus j plus a half, then plus j plus 1/2. I took it from the times 1 minus x over j plus 1/2 square, and that. So we expand this F, or let me go do the n minus 1. So that I don't take much space, minus n j plus a half plus j plus a half 1 minus x over 2 j plus 1/2 square. So j plus a half and j minus a half, so these cancel. This will be, and let me take n out, so n square 1 minus 1 over 2 n x over j plus a half. Square. Meaning f is 1 over n square, 1, let me write upstairs here, 1 minus x over 2n j plus a half to the power minus 2, which means this is, I am looking for the linear term in X. So it is 1 over n square, 1. I am expanding in the binomial series, and I will take only the first term, plus minus 2, so it is plus 2x over 2n j plus a half. This is equal to 1 over n square plus 1 over n cubed, 1 over j plus a half times x. This is equal to a plus bx. A is 1 over n squared, as you see it here, and b is equal to what? 1 over n cubed, 1 over j plus a half. So we will take a and b, put it into here. For this, I must erase something. All right, let me say again. We expand this term to this form, and if we do it like this, A2 has this combination. The idea is to find A and B. This is what we did, expanded and found A and B. Let's get to A2. I'm erasing this F now. I don't need any of this. All right. A2 is equal to minus 1 over 2 n cubed j plus a half plus 3 over 8 a square. A square is 1 over n square, so it is 1 over n to the fourth is equal to let me take 1 over 2 out and 1 over n cubed out. So it is 3 over 4n, this term, minus n cubed, 2n cubed is out, 1 over j plus a half. A2. Now we will compare it with the fine structure and energy. Remember, this is E over mc square. So to power x square, or alpha to the fourth, E will be E alpha to the fourth power will be what? mc square times A2. mc square A2 times alpha to the fourth. So mc square alpha square, so mc square alpha square, and we get 1 over 2, that's epsilon. Then we are dividing it by n square. Then we have another alpha square. We are dividing it by another n. This is simply our coefficient n. The rest is 3 over 4n minus 1 over j plus a half. And now we compare it with the fine structure shift. It is exactly the same. This is nothing but delta E1 fine structure. So where is our energy equation? So E then is equal to ENJ is mc square minus E0n. This is the hydrogen energy plus delta E1 Fs computed for that n and j with that. Okay. So we have expanded this formula. The x is alpha square to alpha to the fourth, and we compared it with the exact the alpha to the fourth term coming from the Dirac exact energy eigenvalue with what we have computed in this video. So it's good that it agrees perfectly. Okay, thank you.